Okay, let's begin our lesson. So for right now, we talk about how to fabricate the M1, metal one. So right now, I use this simple structure to let you have the sense. What does that mean, interconnect? So you see, I just, for example, M1, and then it's followed by VL2, and then followed by M2, okay? So you see, today, if we assume the metal one is the green layer, green layer is a very, very long metal line, okay? So it's a global interconnect. But we don't say that. We just need to know the metal one means this metal layer is a very long metal line. So you see the green metal line is a very, very long metal line. So we write down M1, okay? And today, where is M2? Right now, I assume the M2 is this red metal line here. This red metal line here. I define it the M2. So you see, M2 is also a very, very long metal line. It's the global interconnect, okay? And today you see, how can I connect between M1 and M2, okay? M1 is for this direction. Then M2 will be another direction here, okay? So you see, this one, for example, this one is horizontal and another one is the vertical direction. So the direction is different. And how can I connect metal 1 and metal 2? How can I do that? I need to use the veer. So you see here, veer. I use the veer to connect metal 1 and the metal 2, okay? And maybe this veer is, I cannot show you veer, or maybe here. Okay, maybe I can assume this one is metal 2. Don't worry about that. Okay? Or I can assume this yellow one is metal 2. So you see today, how can we connect this yellow metal 2 or metal 2 and to the metal 1 here? I use the veer, or I use the veer 2 or the local interconnect, a very short metal line to connect between this yellow one and to this green one. Okay, so can you understand? So we write down M1 and 2, and between M1 and 2, we need to use the VL2 or VL2 to connect between metal 1 and the metal 2. Okay. Also, maybe I need to change, or maybe I use this one. Metal 2 is here. Okay? Because you only see the VL, you see the VL2, or you see the VL2 here, right? You see the VL2, and VL2 is used to connect between metal 2 to the metal 1, okay? And also you need to know metal 1 and metal 2, they align to the different direction. And between metal 1 and metal 2, we need to use this veer to connect between metal 1 and the metal 2, okay? 这个 veer 有点像是一个房子的柱子，有没有？它把两个楼层把它连接起来。所以 veer 2为什么它一定是 local interconnect？ 因为它就像是房子里面两个楼层中间的柱子嘛，所以它一定很短嘛，它是不是？然后那你说其他梁一定是很大的梁，它一定是贯穿整栋房子，所以其他的梁是很长的。其他的梁就像 metal 2或是 metal 1都是很长的 metal line， 只有中间这个 veer 像是柱子，像是整栋大楼的柱子，所以它是很短的。OK， so I just want to let you know, for two metal layer we must have the veer. And the purpose for the veer is to connect between the first metal and the second metal. Okay. For example. Okay. So right now, this is the top view. This is the top view for the metal 1. For the metal 1. Okay. And we have the tungsten plug or the veer 1 here. We have the veer 1 here. So right now we have the metal 1. We have the metal 1 on the top of the veer 1. Okay. We have the metal 1 here on the top of the veer 1. Okay. So the metal 1 here. For the technology now of 0.18, we still use the aluminum. We use the aluminum for the main metal material. Okay. So right now, after we fabricate the metal 1, so how about the next one? How about the next layer? The next layer will be the veer 2, right? So you will see. So for the following page, we need to fabricate the VR2, but the process just the same, just repeat it again and again, okay? So we don't go through the detail. VR2 just like the VR1, okay? VR2, where is the VR2? VR2 is here. VR2 is here. Just as we mentioned, we deposit the oxide, we pattern the oxide, and finally, we need to put the tungsten into the VR2, okay? The same process, okay? So after we deposit, after we deposit the oxide, etching the oxide, and then we have all of this area. So right now, we can deposit Ti and Tin, and then followed by tungsten into this small area, okay? So until right now, we already finished the VR2. Or you want to say tungsten plug is fine, okay? You can say tungsten plug, or you can say it's the VR2, okay? So VR2 is the green, the blue color I mentioned here, okay? And I don't write down the purpose for the Ti and Tin, okay? You already know that, okay? So right now, after we finish the VR2, so what is the next one? The next one, we need to deposit the metal again, right? Because this is the B2 and this is M1. So the next thing we will going to fabricate the M2, okay? M2. Okay. Also, you can see the sequence here, okay? Blue one is the VR, so the VR1 and the metal one, and then followed by VR2, M2, and the VR3, okay? So M2 here, M2 just like the M1, the same process flow, okay? The same process flow. The first layer, Ti, is the adhesion layer, and aluminium is the main metal material, and the Tin is the arc material, okay? So they are the same. So the metal 2 has the same material system as the metal 1, the same process, okay? So I didn't go through all the detail because everything is the same for the backend process, okay? Okay. But I can show you, right now we use the aluminum, right? Right now the interconnect material, 金属的内连线, interconnect. For the interconnect material, for the main metal material, we use the aluminum. We use the aluminum because right now we talk about the process flow large or equal to 0.18 micrometer. And the time it's before the year 2000 or 2000. The year is 2000, around 2000. So it's 20 years ago or 20 years ago. But today, if you fabricate the chip, so today maybe for some purpose, if you fabricate the chip with the technology node of 0.18 micrometer, you will still use the aluminum, okay? So maybe although right now it's 20 years or 20 years later, but today for some electronics, if you need the mature process flow, you only need 0.18 micrometer, or maybe who knows, for some toys or some simple electronics, or maybe you will still use the aluminum, or because the technology node is large or equal to 0.18 micrometer. 同学在记材料的时候，有时候你不要只记最先进的材料，因为最先进的材料只用在哪里 ？AI 只用在最先进的手机。那其实你要记得，可能这材料的这一些历年的发展，其实你都要知道，因为未来你不是只有负责3奈米、2奈米、1点多奈米，未来你如果是负责比较成熟的部门，或者是做其他的运用，其实你会用到比较大的元件尺寸的时候，你的材料系统是完全不一样。所以通常我们都会知道哪些材料系统是运用在哪些制程节点上面。Okay, I just want to show you. You need to know all of the material system. Nobody can guarantee you will go to the latest department. So maybe if you are responsible for the 0.18 micrometer, you need to remember you use the aluminum. Okay? And after after 2000 year, when the technology no smaller than 0.13 micrometer, you need to know right now we already use the copper. We use the copper to replace of the aluminum. Okay, so for the metal material, for all of this metal 1, metal 2, we use the copper. We use the copper. Okay, and for the beer, aluminum will use the tungsten for the beer, right? For the aluminum, we use the tungsten plug. Okay, and for the copper, for the first layer, the first local interconnect, for the first local interconnect, we use the tungsten. For the upper, like VL1, VL2, VL3, we can use the copper to fill in this plug. Okay. So we use the copper. Okay, and then when it move on to 7 nanometer. Okay, although the main metal materials still use copper, but right now we induce cobalt. We induce the cobalt layer. Someone may say, we don't use the tungsten plug for here. Instead, we use the cobalt layer for the local interconnect. Here, we use the cobalt. And also, someone may say, we don't use the TA and TAN for the diffusion barrier. Instead, we use the cobalt to become the diffusion barrier for the copper. Okay, so I just show you. I cannot show you the detail of the cobalt distribution. I have no idea. One day you can. Oh, don't tell me it's a secret in the IC fab. So don't tell me. But I just show you the cobalt we use right now for very, very advanced chip. We use cobalt, but cobalt is not the main material. The main material, we still use the cobalt. The main material, we still use the copper, Cu, and the Co we only use for here and maybe here, okay? But to where, I don't have any idea about that, okay? 对于 cobalt 在比较先进的制程7奈米、5奈米以下那有些人说在这一层第一层 local interconnect 课本说的 local interconnect 这一层有人说全部换成是 cobalt 那有些文献甚至说从下面可能到 metal 5都是使用 cobalt 文献上面说的。那有些文献甚至说可能没有到 metal 5这么高都用 cobalt 它可能用在哪里？假设这根是铜，它用在铜的什么 diffusion barrier 铜的 diffusion barrier 它不用 TAN 它直接用 cobalt 所以这有没有一点混乱？有，为什么？因为这些都是业界的机密所以它不能告诉你它的 cobalt 到底是用在哪里，到底是用在第1层到第5层，还是第1层到第4层。所以你大概有个概念，你要知道说我们已经换新的材料了为什么？因为 cobalt 它的填洞的能力更好比 tungsten 更好，所以它可以用来填洞。但是到底填到第几层这个我也不知道现在的文献写的也很众说纷纭那未来你知道也不要告诉我因为那是公司的 secret 你也不用跟我说所以只是告诉你你知道有这个新的材料那我相信对于业界而言它也不是所有的 generation 全部都是 metal 1到 metal 5全部用 cobalt我相信不同的产品它的规格是不一样的所以这边给同学做参考未来实际是什么你就看你的部门怎么做你就会知道了 OK so right now I just show you I can show you the new material cobalt but I cannot tell you maybe cobalt is from metal 1 to metal 5 or metal 1 to metal 3 I have no idea okay it depends on the generation of the chip and depend on the company you're working for so I have no idea I just show you the material system right now we develop cobalt so cobalt will be used for this interconnect okay and finally this cross-section view this is the cross-section view for the chip and this is the cross-section view for the chip of 0.18 micrometer okay so right now you see here is PMOS and here is NMOS okay so we see all of this interconnect But right now the metal is only only 4 layers of the metal, right? 4 layers of the metal, okay? So on the top, you see we have the bonding pair metal. Here is the bonding pair metal, okay? Usually bonding pair metal is very soft. We use the soft material like the aluminium. Of course, for the 0.18 micrometer, the metal material is also aluminium, okay? And then we use the probe, or we can, I don't know how to draw the probe, maybe. Or we use the probe, or 探针, or we use the probe to detect, to come into contact with this aluminium bonding pair. And then we can provide the voltage and then measure the current from the bonding pair here, okay? So today, after we finish this chip, so for the final test, we use the probe 探针. We use the probe to come into with the bonding pair, and we can provide the voltage, apply the voltage, and measure the current, for example, okay? But of course, this is after all of the chip is finished. But in truth is, after we fabricate the transistor, we will do the measurement, okay? And maybe after the metal 1, we do the measurement again. After the metal 2, we do the measurement again. And this is the final test, after we finish all of the semiconductor processing for the chip, we do the testing again, okay? So I just show you for the bonding pair. The bonding pair just like the electrode here. 这是我们探针下针的地方, okay? So here, we have the passivation layer. Usually passivation layer is nitride, very hard material. We use the hard material to protect our chip, okay? So nitride is the good choice, okay? So you see for the semiconductor industry, the material is very simple, right? For the hard material, we will use the silicon nitride, right? Because it's easy to deposit, and the material system includes the silicon, so it's compatible with our silicon wafer, okay? So that's the reason today, if you want the hard material to become a protecting layer, for example, for a preservation layer or protecting layer, you will choose silicon nitride, okay? Silicon nitride 这个材料至少它是跟我们 CMOS 的制程是相容的，相容代表说，业界有使用过这个材料，而且常用，所以业界对于这个材料怎么长、怎么移除，都非常的熟悉，所以业界通常不太会换材料，因为要开发一个新的材料，又要整合其他的制程，非常的困难。Okay, so we choose the silicon nitride as the preservation layer. Because as we know, nitride material, silicon nitride is a very hard material. So we use the silicon nitride to protect the chip from moisture. We don't want moisture. We don't want the chip is damaged. So it can protect from scratch, 被刮伤 and contamination, 避免其他金属啊或是灰尘去污染到晶片 ，OK？ So here we only open this space for probing, okay? We only open this bonding pad this area for the electrical probing, okay? And for other region, other area we need to use the silicon nitride to protect the underneath chip, okay? So only the small area, or maybe this bonding pad is the square, in shape, and we use the electrical probing to detect the signal from this transistor, okay? And when I was your age, I also use this. I also see the textbook, and for the textbook, I also see this diagram, okay? And then many years ago, I memorized all of this design because I think maybe it's important because it's the the IC fab, so I need to know how to draw this one. I'm so stupid. I memorized this image. But right now I can tell you it's not so important. Don't you memorize how to fabricate it. You memorize the material system and you know why, you know purpose, but you don't need to memorize this figure because I can show you how everything is changing, right? You see, this is the real TEM image for the Intel 22 nanometer technology. No, you see the interconnect just seems very, very different with our textbook, okay? So I want to show you, you don't need to memorize the layout for the backend process. Don't do that, okay? Don't do that. Don't like me, I'm very stupid to memorize all of the layout for the 0.18 micrometer, okay? You see, this is the possession view for the interconnect for the 22 nanometer, okay? So you see, for the 22 nanometer technology, for the Intel chip, you see, right now we have a metal line, and we have a metal line. You see, we have the metal A. So right now, we can fabricate the 8 layers of the metal line. Okay. And right now, for nowadays, we already have 11. I believe we already have 11 layers of metal, 11 layers of the metal. Okay. And this pitch may be the metal pitch, or the metal pitch. So the first layer of the metal is 19 nanometer. But for the next generation, chip, for the Intel, they have 22, and the next generation chip is 14 nanometer because we can times 0.7 times. You times 0.7, you times 0.7. So 22 times 0.7, it will become like 14 nanometer. Okay. So this is how we define the technology now for the next generation chip. We just times 0.7. Okay. So you see. So let me see. You see. Okay. So for the 14 nanometer interconnect. Okay. So usually, you will see, the metal pitch will also scale down, will also be scaled down. Okay. So this is the M1 pitch, and then when it move on to 14 nanometer, you see the M1 pitch will reduce a lot, to 50 nanometer. Okay. So that's the reason I show you why right now the total yield will be dropped due to a very, very small metal pitch. It's very difficult to fabricate the small metal pitch for the VL1 and M1. All of this button there, very, very difficult to fabricate it. Okay. Because you can see the pitch become smaller. Okay. 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 Let's see. Let's watch the video, and you can review all of the process flow again. Simply. Okay. And only 2 minutes. Let me see. Only 2 minutes, and we will show you the process flow again. Okay.
Now, let's take a look at a simple semiconductor process flow. First, a layer of silicon dioxide and polysilicon is grown on the surface of a wafer in a temperature-controlled furnace. After the films have been grown, the wafer is given a photoresist coating. Then, the wafer is exposed to UV light that shines through a pattern defined on a photo mask. The irradiated area is developed afterwards. Lithography is the crucial step that transfers all circuit patterns from the mask to the wafer. the proper combination of advanced exposure conditions and resist development ensures that the pattern faithfully matches the design requirements. After the pattern has been defined, the wafer is ready for dry etching. Dry etching is another key factor for the final characteristics of the device. A gas reaction removes specific areas of film to define the device's pattern. Any unprotected polysilicon and silicon dioxide will be removed. The wafer is then cleaned by chemical solutions. Any remaining photoresist is also removed at this time. The gaps in the outer layer allow ions to penetrate the surface of the wafer. This doping process forms sources and drains. After ion implantation and annealing, a metal such as tungsten is deposited on the wafer as a contact material. At this stage, because the wafer's surface is not a perfectly flat plane, chemical-mechanical planarization is applied. This removes protruding bumps and evens out any irregularities, making the wafer flat. Finally, the transistor is complete. We operate a fully automated 300mm memory wafer fabrication facility with the highest machine-to-human ratio in the industry. At any given time, our in-house intelligent automation system controls more than 400,000 operations to make more than 60 products. In this advanced factory, equipment control, wafer dispatching, and wafer transportation are controlled by the automatic system. Wafers are efficiently handled in front-opening unified pods or FOPs. After the FOP has arrived at the equipment load port and the recipe body has been validated by the recipe management system, the job is executed by the equipment. As the machine processes the wafers, 600,000 equipment parameters and 150,000 wafer engineering data points are monitored in real time to ensure optimal equipment status and wafer quality. The system automatically detects any exceptions and triggers appropriate predefined follow-up action plans.
Okay, so if you are interested for this video, you can watch it later, okay? So I just want to remind you all of the module we mentioned, okay? So right now, until right now, we already fabricate our chip. So we need to do for the final testing, okay? So for the final testing, we call it WAT. So WAT means wafer acceptance test, okay? WAT can be done for many steps, okay? It means after the transistor is finished, we do the WAT, we do the electrical test, and then we do the WAT means we do the electrical test, we do the electrical test. WAT means wafer acceptance test. We need to do the electrical test in order to know the transistor at the good performance or bad performance. So you need to do the WAT. So we do the WAT a lot. Okay, not only after the semiconductor processing, but maybe after the transistor, we do it again. And after metal 1, after metal 2, we need to do the WAT a lot in order to make sure which metal line and which process flow is going wrong. Okay, so we need to know what's happening for each processing step. So that's the reason we do the WAT a lot. Okay, in industry we do have the department we call it WAT. So it's a very good department, right? Because for the WAT, so they will do the measurement and they will gather all of this electrical performance. They have all of this data, and then they will analyze all of this data, and then they need to give a report about what happened to our chip. Okay, so WAT is also the department's name. Okay, so next time when you hear WAT, you need to know we do some electrical measurement, and we have some data, or we need to download all of this data to see if the transistor has good performance or bad performance. So WAT is a department, or it can be a department. It can also be a data, the electrical data to show you, or maybe ID, or maybe the ID, the on current, the off current, and all kind of the parameter, or we can obtain from WAT. Okay. And this is a picture from my lab. Or you see all of this electrical measurement is the same as the IC fab company. Oh, I don't say which one, but I can show you all of these electrical measurements are the same. Okay. Oh, but one thing is different is the probe station here or the probe station here, or inside this probe station. Or for usually in the school, or we need to do the measurement by human, by ourselves, right? Or we need to do the measurement. So one time we only can measure one transistor, or because you have 1, 2, 3, 4 probe, right? You see the yellow one, 1, 2, 3, 4 probe. 4 probe only for one transistor, right? So one time we can only measure one transistor. 这个黄色都是一根针，所以总共1、2、3、4根针，有没有？4根针，4根针只能下一颗电晶体，所以这为什么是人工的？量测你一次只能量一根电晶体。However, in the industry, in the IC fab, they have so many probes, so they can measure tens, maybe hundreds transistors at one time. Okay, so they save a lot of time. Okay, but for the school, we only can measure one transistor at one time. Okay, however, we do have the same electrical measurement tool. Okay, so this line for your reference. Also, I want you to memorize WAT, because in the future you will hear WAT a lot. Okay, you will hear WAT, or maybe nobody knows what does that mean. WAT for us, we know it means a department. It means you do the electrical measurement. And right now we have some data. We need to download all of this electrical data. So we know WAT means we have some measurement data, electrical data. Okay. Okay. So far so good. Okay. Before we move on to the next slide, let's do a roll call. Okay. So please log in your Lumia, let's do a roll call. Okay. Okay, so let's move on to the next slide. The next slide we are going to talk about the detail about the oxidation. The oxidation in Chinese, so you can memorize the Chinese. Okay? So for the oxidation, you can memorize the Chinese. But of course, I believe for the terminology, English is much more important. Oxidation. So in IC phase, we mention oxidation. Okay, so we don't say Chinese. Or in industry, we only say oxidation. Okay. Okay. So later I will show you how the different outside, how the different outside. For here, so there are two kinds of outside. The first one is thermally grown outside, thermally grown outside, and the second one is CVD outside. And today, the oxidation means thermally grown outside. Today, the oxidation only means thermal grown outside. Okay, you need to make it clear. Today, the oxidation only means thermally grown outside. Or it means today I want to grow outside. Thermally, I use the high temperature to grow outside. Okay, so sometimes this outside we call it thermal outside. Thermal outside. It's also very common to hear thermal outside. Okay. So today, thermal outside, or thermal grown outside, they are the same thing. It means I deposit the silicon dioxide by using high temperature as high as 1,000 degrees Celsius. 1,000 means around 1,000, maybe 1,100 or maybe 950 degrees Celsius, around 1,000. You only memorize around 1,000. Okay? So oxidation means thermal oxide or thermal grown outside. It means we need to use high temperature. Okay, you need to remember we use high temperature to grow outside. Okay, so the oxidation means we need to use a very high temperature. The temperature is around 1,000 degrees Celsius. It's the thermal oxide. It's the thermal grown outside. Okay, so usually we prefer to say thermal oxide. Okay, but the textbook write down thermal grown outside. I think it's the same idea or the same idea. So don't worry about it. Thermal outside or thermal grown outside, just the same or the same thing for you. It just means for today the process flow we call it oxidation. Okay. And then for the CVD outside, the CVD outside is the deposit outside. CVD outside is the deposit. Deposit outside. 沉积 CVD outside is the deposit or deposit outside 沉积的氧化物 or deposit outside CVD outside because we use the deposition we go to the thin film module, right? We go to the thin film area to deposit the outside. So for the CVD outside, it's the deposit outside. Okay? And do you still remember when we talk about oxidation? It means we go to the diffusion module, right? We go to the diffusion area to do the oxidation. Okay, so this outside we call it thermal outside. Okay, so you need to make the difference between CVD outside and the thermal outside. Okay, so we use the oxidation to grow thermal outside. Okay, so the next slide, I will show you the difference between thermal outside and the CVD outside, or you can say it's the deposit outside. Okay? So at first you need to know when we say thermal grown outside, right now we are located in the diffusion area. Okay, and today if we mention CVD outside, deposit outside, right now we are located in the thin film module, thin film area. Okay, so you need to make difference. Okay. Okay. So this slide, I will show you the difference between the thermal oxide or the thermal oxide and the CVD oxide. Okay. So thermal oxide is on the left side and the CVD oxide is on the right side. Okay. And bare silicon just means blanky, 空的 or blanky, bare just means blanky silicon or blanky silicon. Okay. So this is the silicon wafer or the silicon wafer. So this is the silicon wafer. So the yellow one is the silicon wafer. So the thickness is here. Okay, thickness is here. So today, if I use the oxidation. Today, if you use the oxidation, I want to grow the thermal oxide. I want to grow thermal oxide. How can I do that? It's very simple. I use the furnace. I use the furnace or over tube, and then I just put the oxygen into the furnace, and then thermal oxide means high temperature, right? So under 1,000 degrees Celsius, around 1,000 degrees Celsius. I just want to show you it's a very high temperature, okay? So maybe 1,100, maybe 950 degrees Celsius, around 1,000 degrees Celsius, okay? Very simple process, right? I just put the oxygen, and then what happens? The oxygen will react with silicon wafer. Oxygen react with silicon wafer, okay? So right now we go through the details. You see how very simple. For the first one, oxygen is from gas phase. It means oxygen is from outsourcing, right? Oxygen is from gas phase. It means I put the oxygen into the furnace. So oxygen is the outsourcing, right? And then the next one, silicon is from substrate. Silicon is from substrate. Also, it means I put the oxygen into the furnace, and then oxygen reacts with silicon wafer, okay? So today, if the oxygen must react with silicon wafer, so we will consume the silicon wafer, okay? We consume the silicon wafer because oxygen reacts with silicon wafer. So right now, you see the silicon wafer, the thickness of the silicon wafer will be reduced, right? The thickness of the silicon wafer is reduced, right? The thickness of the silicon wafer is reduced compared to the original silicon wafer, right? Why? Because the oxygen reacts with silicon to grow silicon dioxide. Okay, so far so good. So 1, 2, 3. Oh, right now 1, 2, 3. Oh, you can see the picture. If you can understand the picture, you don't need to go through the detail. Okay. So today we provide the oxygen to react with silicon wafer. So the silicon wafer thickness is reduced. Okay, because we already grow the silicon dioxide. Okay, and then this process is under high temperature. The high temperature like 1,000 degrees Celsius. Okay, and usually this thermal oxide. Has higher quality. Or it's very important. Usually it has the higher quality, and also the growth rate is lower. So today, if you want to deposit or you want to grow some material, if you want to have high quality thinking, you need to remember the growth rate is always slow. Okay, growth rate is always slow in order to have the better thin quality. If you want to have the high quality, growth rate is much slower. Okay, so if we use the oxidation, this process, the growth rate is slow. But don't worry. Usually, when we use the thermal oxide, it means the oxide thickness is thinner. When oxide thickness is only 1 nanometer, like the gas oxide, you don't need to worry about the slow growth rate, right? Because the thickness of gas oxide is only 1 nanometer. So the lower growth rate doesn't make any difference, right? It's not a big issue, right? Because we only want to grow 1 nanometer silicon dioxide for the gate oxide, or for the very thin layer, and with a very high quality. So we will use oxidation. We use the thermal oxidation to grow silicon dioxide. Okay. Okay. So right now, we talk about the CVD oxide. CVD oxide is the blue color or blue color writing. Okay. So right now, for the CVD outside, we need to go to the thin film or thin film module, thin film area. Okay. So the tool to deposit the outside will be CVD. CVD is the tool. Tool name of CVD is the tool. So we use the CVD to deposit the outside. So that's the reason we call it CVD outside. 这个 CVD 是一个长薄膜的基材，所以我们叫它 CVD outside。它很明确告诉你，它是用 CVD 长出来的 outside。Okay? For the CVD outside, you see oxygen and silicon are from gate phase. What does that mean? Today we want to deposit the silicon dioxide by CVD. So I will put the silicon and the oxygen, okay, into the CVD chamber. Okay. So today, the silicon and the oxygen is from outsourcing. Okay. So oxygen and silicon are from gate phase. It means I need to put silicon and oxygen at the same time. Okay. But of course, the precursor is not pure silicon. I just want to simplify it. Okay. The precursor is not a pure silicon. Later, when we talk about the CVD, I will show you the real precursor for the silicon. Okay. Right now, I just want to make it simple and clear. So I write down the outsourcing is the silicon. Okay. Later, I will tell you details. 我们的确silicon 跟 oxygen 它的来源都是从我们外部通路的，但是我们一般是通路气体。所以这个实际的 precursor 我们之后再讨论。那我可以告诉你 ，silicon 跟 oxygen 是从外部通入 CVD 的这个 chamber 里面。但是实际的 precursor 不是真的只有 silicon 它可能是一个 silicon 的有机物。这个之后我们再讨论。OK。So I just want to show you the silicon and oxygen is from outsourcing from gate phase. Okay. So today the silicon is from outsourcing. So we don't consume the silicon substrate. We don't consume the silicon substrate. W/O is without, or W/O is without. It's also very common to see in industry. Okay. So without, just for your reference. Okay. This one just for your reference. We use W/O a lot for our report. It just means the without. So today the silicon is from outsourcing. So you see, for the silicon wafer has the same thickness as the original silicon wafer, right? So silicon wafer has the same thickness with the original silicon wafer. Okay? So for the CVD outside, you see, the silicon wafer thickness is the same, as the original silicon wafer. Okay? Because we don't consume the silicon wafer. We don't use the silicon wafer to provide the silicon atom. Okay, the silicon atom is from outsourcing. Okay, and today only lower temperature is used. So maybe 400 to 600. Maybe so only 400 to 600 degrees Celsius is quite enough. Why the temperature is different? Because the tool, we have different kinds of CVD, and we have different kinds of precursor. Okay, so due to different tool and due to different precursor, so we have a range of the temperature. Okay, so usually 400 to 600 degrees Celsius is good to deposit on the outside. Okay, so lower temperature will be used. And higher growth rate. The growth rate is higher. so quality is not good. I mean, it's not as good. It's not as good as the thermal oxide. Okay, but in industry, of course, they can deposit the CVD oxide with high quality, but not as good as the thermal oxide. Okay. Okay, we take 10 minutes for a break. Okay, any question you can discuss with me.